So this is lecture 4B on differentiability. Welcome to this lecture. So this basically now tries to extend the knowledge about differentiability that you learned in first year calculus, right, to the case of a multivariable problem. Again, we're going to be more or less dealing with two variables, but the extension to more than two variables should be relatively straightforward. So the material for this lecture comes from section 15.3 of the text, but I've also included additional material which is not in the textbook. The objectives of this teaching module or lecture are to extend the concept of differentiability for one variable to the multivariable case. So the concepts are differentiability and its relationship to continuity. As usual, the second slide is just an overview of the slide contents. I'm not going to basically spend any time on this slide. We'll just move on. All right, so let's quickly review what you learned last year with regards to differentiability of a function with one variable. And so the definition basically can be written in two different ways. So we can either say that the derivative of the function of f of x is f prime x, which is a limit of fx plus h minus fx divided by h as h goes to 0. Or alternatively, by bringing f prime x to the other side and basically creating a common numerator term, we can express it as the difference between fx plus h and fx plus hf prime x divided by h, and the limit of that needs to go to 0. Right, so this basically can be done provided the limit exists and x is in the domain of f as a function of x. If f prime a exists, we say that f of a is differentiable at a. If f of x is differentiable at every point on an open interval I, we say f of x is differentiable on I. All right, so you'd have to basically test out every point to be able to make that assertion. All right, so you might ask yourself, why do we write it in two different ways? Well, the alternative expression invokes geometric principles which are intuitively easier to grasp. And also, the definition for differentiability for a function of two variables follows naturally from the definition of differentiability for one variable, as will be shown next. So let me just sort of spell out in more detail the alternative definition. And so I'm going to write it now in a more concrete fashion, and we'll make reference to the picture on the right-hand side. So let y equal f of x be an element of an interval I, be a function of one variable. Suppose that the derivative f prime exists at the point x equals a. And now what we do is define the linear function, which actually is a tangent line. And it's basically f of a plus f prime a times x minus a. This is more or less the Taylor series expansion, right, of the function where we only retain the first two terms, one involving the function itself evaluated a and the other one involving the first derivative of the function evaluated a times x minus a. We say that f is differentiable at a if the limit of x approaches a of e of d, which we'll explain next, divided by d xa equals 0. E of d is the difference between the function evaluated x and the linear approximation to the function at a particular position x, right? And d x of a is basically the distance between the point of interest, which is at x equals a, and an arbitrary point x. So E of d represents the difference between the value of the function on the curve and on the tangent line. And the meaning of dxa is the distance between arbitrary point x in an element of the interval I and the point of interest x equals a. If either derivative f prime a does not exist or the limit is not 0, then fx is not differentiable at a. Okay, so that's a most important point to retain. Now, just for interest, you'll notice that the expression of limit xa ed over d over xa equals 0 is obtained by replacing x with a and h with x minus a in the previous expression for the limit, that's limit of h approaching 0 of x plus h minus f of x minus h f prime x over h which is from the previous slide. So now let's look at this picture, because more or less everything on the left is depicted in this picture. And in fact, there was a simulation, interactive simulation, that you can basically make use of. We'll show shortly. So here's the tangent line. Here's this error we're referring to. This is a point of interest, which is at x equals a. This is some arbitrary point of x. And so what we're going to basically do, approach this point from both directions. This is just a snapshot for a particular instant. And so as you move closer to this point, then you're moving down the line, and this error becomes vanishingly small. And so what you're looking at is to make sure that this error collapses faster than the value that h is going to 0, right? In which case we can guarantee that the limit of this ratio is equal to 0. All right, so this is an example where if you were to look at every point and put a tangent line every point, effectively you'll find that this condition is always satisfied, that is, it's equal to 0, which means that it's differentiable for all points in the interval of all points x interval I, which is basically this that we see here. All right, so this is now the actual simulation or interactive simulation you can run. I've basically just shown different things. These are two different functions that you can select, one which has continuous derivative and one with a discontinuous derivative. These are toggle switch. You turn them on and you'll get a different picture. The t, the a, the b, s, and the p here basically are described here. This, of course, is for the continuous derivative function. This is a discontinuous derivative function. T modulates the direction of the red vector. So effectively, this tells you from what direction you're approaching the point A. A is a position on the x-axis. S modulates the length of the red vector. So effectively what it does, it narrows the circle or the distance in which you basically approach the point of interest A. And P modulates the length of the red vector. So for the continuous case. So S is for the discontinuous case, P is for the continuous case. So as you go through here, this is a discontinuous case. You'll notice that this thing will be a perfect fit, and then it suddenly jumps to this side, which means it doesn't know what to do at this point. So at this point here, we know differentiability doesn't exist. I mean, this essentially is a cusp point. Anyways, by all means, play with this, that you can understand that when we're dealing with differentiability, ultimately what we're interested in is, can we basically approximate the curve at a given point by a tangent line, right? That's more or less is what we're trying to do. All right, so let's extend this now to the differentiability of a function with two variables. Unfortunately, the book's definition is a little bit opaque, and I'm going to convert this into a form that looks similar to the case that we looked at for differentiability with one variable. But more or less, you can sort of see a certain pattern evolving. In the case of two variables, we're basically perturbing the value of x, that is, a is changed by a small amount, the y is changed by a small amount, and we're taking that and subtracting the difference value of the function evaluated at ab. Now this basically is more or less an approximation to a surface. Don't forget, a function of two variables is a surface. So this expression here is nothing more than a tangent plane. It's a tangent plane because it's linear in delta x and it's linear in delta y. And these are residual error terms, right? So the function is differentiable on an open set R if it is differentiable at every point of R. So this is the book's way of doing it. The way we're going to do it is a little bit more elegant and follows naturally from the one variable case. So this is a picture that you showing two cases, one where the surface is smooth and one where it has a point in it. So in this case here, you will notice that you'll be able to turn the simulation. You'll make this patch smaller and smaller. So in the limit, that patch appears to get flat and flatter. So eventually it appears like it's a tangential plane, and the tangential plane basically is defined at the top here. In this case, no matter how small you make this, in other words, this circle area gets smaller and smaller, and eventually it just encircles the peak. We can never make it a tangential plane fit at the top, because you've got these two different regions who's basically got different characteristic shapes. And so again, similarly here, you've got the two cases to consider. You've got S and P, one being the continuous case, one the discontinuous case. You have the toggle switch here where you can look at one or the other. And you can basically look at this interactive simulation to visualize what's happening. On the next slide, we'll show a little bit more detail of what's going on. Okay, so here's now the definition when we move to, for differentiability, when we move to two variables. Now, just sort of point your attention now to the fact that the L function, which previously was one-dimensional, is now two-dimensional. And you'll notice it's a Taylor series expansion. We'll talk more about this in a few lectures, but you can see there's a constant term. But now there are two derivative terms, one involving the partial of f with respect to x, evaluate ab, and one is the partial of f with respect to y, evaluate ab. And this is along the x direction, and this is along the y direction. So this is, in fact, the equation of the tangent plane, right? Assuming that these partial derivatives exist. We say that f is differentiable ab if the limit of xy approaching ab, ed divided by dxy ab equals 0, where ed is the difference between the value on the surface and the value on the tangential plane. And d is going to now be a little bit different. It still is a distance, but because the distance is moving towards a point of interest, which is AB, from all possible directions in the xy plane, then the simplest way of defining that distance is the norm, which is basically just the norm of the vector x minus a, y minus b, which would be the square root of x minus a squared plus y minus b squared. We'll look at an example much later on where we basically show how this is done. But that's the natural extension, right? So if either the partial derivatives, fx or fy, does not exist, or the limit is not 0, then f is not differentiable ab. So this is the most important takeaway message regarding how you look at the definition of differentiability of a function with two variables. And again, here basically you have different things you can control. And so a controls the position of a, b controls the position b. So that's the x and the y coordinates. P is the radius of the dot circle, okay? And t basically rotates this black arrow around. So effectively what you're doing is you're approaching from different directions. So if you look here and extrapolate up, this is the point AB at which this is a tangent plane. You can barely see it here. But if you click here, you'll be able to rotate it and see the tangent plane. And this you see here is the error, that is the error difference between a point on the surface and a point on that tangential plane. And we're basically watching the circle collapse, which means this point gradually works in this direction. So long as this collapses to 0 faster than this collapses to 0, then we know the limit basically is equal to 0. So this is actually the formal definition, which is easier to intuitively understand when we're dealing with differentiability with two variables. If we were to make this 3 variables, what would change? Well, we would end up basically with something similar, but we'd end up basically with yet another derivative. Secondly, the distance now basically would be in 3 space. So instead of having 2 components of a vector, you'd have 3, but it would still be the norm. It would be the distance between some point in a volume moving towards the point of interest within the volume. Then you can extend it to higher dimensions. But this is much easier to understand definition differentiability using a geometric approach. All right, so general problem. The conditions of the definition are generally difficult to verify, and so the following theorem is considered. Theorem 15.5, conditions for differentiability. Suppose a function has partial derivatives fx and fy defined on an open set containing ab, with fx and fy continuous, then f is differentiable ab. The problem here is that you have to prove continuity of the first order partial derivatives of the function fxy. That could be problematic, but in some cases it's doable. Now I can also look at a contrapositive argument, and the reason I'm doing this is to point out one specific fact. So if we do contrapositive, you have to work backwards, negate it, and then basically on the other side is a negated version of what was on the forward side for a direct proof. So if we basically start with the condition, if the function is not differentiable at ab, then at least one of the partial derivatives, fx or fy, is not continuous at AB, or there is no open set containing AB such that the partial derivative fx or fy is defined at all points on that set. So when you have a bunch of conditionals like this and this and this, and you negate it, then that becomes basically an OR statement, but of the negated quantities. The not of this, or the not of this, or the not of this. So if one condition is not satisfied, that's more or less it. However, you always have to know what the first part of the statement is. So here it says if the function is not differentiable. Well, you better know it. You cannot assume it. If you don't know it, then you cannot use a contrapositive argument. So that's something to bear in mind. We'll do an example later where we start by knowing what it is, and then we go to show that one of the conditions is not satisfied. That's on the other side. All right, so now we look at the relationship between differentiability and continuity. For one variable functions, differentiability implies continuity, not the other way around. This concept can be extended to the multivariable case and is stated in terms of the following theorem. The proof is given in the book. So theorem 15.6, differentiable implies continuous, says that if a function is differentiable at AB, then it's continuous at AB. The contrapositive argument would be take the end statement, negate it, put it at the beginning, and take the beginning statement, negate it, and put it at the end. So if the function fxy is not continuous at AB, then it's not differentiable at AB. So this particular contrapositive argument is used quite frequently to prove differentiability. So because it's relatively easy to basically show if a function is not continuous. I mean, we'll make use of that quite frequently, at least the contrapositive argument. All right, so we'll do some examples now. Example 1 is the differentiability and continuity of a function using in the contrapositive argument for theorem 15.6. So let's discuss the differentiability and continuity of the function fxy equals 3xy over x squared plus y squared if basically we do not include the point 0, 0, and we stipulate that that function's value is 0 at xy equals 0, 0. All right, so let's go through the process to figure out basically differentiability and continuity. So we notice first of all that fxy is a rational function if xy is not equal to 0, 0. And therefore we know that the function is continuous and differentiable at all points excluding the point xy equals 0, 0. So next thing is at the point xy equals 0, 0, we must determine if the function fxy is continuous. Rule 1 is satisfied, that is the rules of the continuity, there are 3 of them in total. Rule 1 is satisfied, but rule 2 is not, as shown by assuming that the limit does not exist. And you can basically do this by choosing a path y equals mx in the xy plane. Notice here that the order here is 2xy and the order here is x squared, which is the same as this. So it would make sense in this case to choose y equals mx, at least it's one option. You could have also used substitution of variables because we have this x squared plus y squared in the denominator. Anyways, if you make this substitution in, then after simplification, we end up with the expression 3m over 1 plus m squared. The value of m basically determines the path. So in the xy plane, y equals mx. Choose a different value of m, you choose a different path. Since the limit depends on the path, which is the choice of m, the limit does not exist, and thus fxy is not continuous at 0, 0. Therefore, by theorem 15.6, using the contrapositive argument, it follows that f of xy is not differentiable at 0, 0. All right, so when I have basically 2 interactive modules here, all right, so you can look here, for instance, you'll find that, for instance, when you're taking the derivative, you can either, use a technique we developed in the previous lecture, or you can use the exact definition, particularly if you were looking at a given point where the function is not defined, but you have specified a value of the function at that point. So in that case, for instance, this value will be known, and you can compute the partial derivatives directly. So for example, in this example here, right, you basically partial y would basically mean you perturb y and then subtract it from the original value. And then you divide by h. All right, and here basically x is set to 0. All right. Well, if you do that, you'll find you'll end up with x 0 times something, which means you get 0. Similarly, in this case, you basically, this is y. In this case, you'll end up with y in front, y going to 0, and so this will also be 0. So the partial derivatives at the point 0, 0, that's fx, fy, are both defined. Okay, so you can go to this simulation if you want interactive to look at the nature of this function in more detail if you wish. Anyways, I've put it there so that you can look at, and there's really not much to discuss. All right, so example 2, applying the contrapositive argument to theorem 15.5. So the function of x of y equals 3xy over x squared plus y squared if xy is not equal to 0, and 0 if xy equals 0, 0. We actually now have shown from the previous result that it's not differentiable at 0, 0 from example 1. So it's a given because we've already shown it to be the case. Now, according to the contrapositive version of theorem 15.5, we know that one or both partial derivatives are not continuous, or one or more partial derivatives are not defined at 0, 0, right? We know that to be the case because basically it's not differentiable. So now what we want to do is confirm that f and fxy, partial fx and partial fy are defined on an open set containing 0, 0. And we want to determine which of the two partial derivatives is discontinuous at 0, 0. So we just go through a series of calculations then. So the partial derivatives, right, we need to compute at 0. Well, because we've defined the derivative, defined the function 0, we can use the definition of partial to compute what f of y is at 0, 0. So this is the calculation I did on the previous page. It's just repeated here. So this is what it looks like. And for fx at 0, 0, we have this value. So the partial derivatives at the point 0, 0 do exist. Okay, so now basically what we want to do is the partial derivatives over r squared. So outside of this point, this function is analytical, and so we can basically take the partial derivative of this with respect to x and with respect to y. Once we do that, we end up with this expression for f of x and this expression for f of y. All right, so the next thing we do is to make the substitution x equals r cos theta and y equals r sine theta. Why is that? Because the denominator had x squared plus y squared, so let's try it and see if we get anywhere with it. And we're applying the mapping, therefore, that x equals 0, y equals 0, basically transforms into r equals 0, and theta can be anything, all right? So if we take the limit of fxy, right, which is this, and basically make these substitutions in here, then we end up with this expression here, minus this divided by r. If we do the same thing for f partial y, we end up with this expression, and when you make the substitution for x and y, we end up with this expression here. For this case and for this case, we let r go to 0. Theta, sine theta is bounded, cos 2 theta is bounded. R going to 0 means this becomes undefined. Okay? So effectively, basically, this limit does not exist. So note 1, we made use of trigonometric identity to simplify the numerator. So x squared minus y squared is just cos squared minus sine squared, which is cosine 2 theta. So questions, are the partial derivatives continuous? All right, we know already from this we got a problem. So again, the definitions of continuity, the functions fx and y are continuous at point 0, provided the following rules are satisfied. This and this are defined at 0, 0. The limit of f partial x and the limit of s exist. And thirdly, the limit of fx is equal to fx 0, 0, and the limit of fx fy is equal to fy 0, 0. Rule 1 is satisfied since the partial derivatives exist at 0, 0. According to Rule 2, neither limit exists. Both functions are not continuous. Okay, so we basically have used the contrapositive argument knowing full well that we knew that it wasn't differentiable, and at the outcome we knew that something would have to give, that something basically was not continuous. It turns out in this case, both functions are not continuous. All right, so now we're going to look at the applicability of theorem 15.5, show that it's not possible to prove that fxy is the absolute value of xy is differentiable at 0, 0, since one or more of the conditions required to apply theorem 15.5 is not satisfied. So we just basically are going to work through this problem. I've put a diagram on the side here to indicate, the regions of interest. And so, for instance, everything in this region or this region or this region or this region is all right. The problems will lie along the y-axis and along the x-axis. And it turns out that the origin, it's almost like a special case. All right, so the first thing we will do basically is restate this function in the following form. We mentioned earlier that anytime you see the absolute value of some function, you can replace it by the square root of the square of that function. Right, this is the simplest way to work with it because we can take derivatives of this. We cannot so easy take derivatives of this. We don't know how to interpret it. So first thing is to compute the partial derivatives at xy equals 0, 0. So we're going to make use of the actual definition, right? And the definition here would be to evaluate the value of f at 0, 0, which is easy enough. It's 0, right? So f partial x would be perturb the x value, subtract it from the value at 0, 0, and divide by h. Similarly, we do the same thing for the definition of partial f with respect to y. Perturb the y value, right? Value the function of f, subtract it from the value of the function at 0, 0, divide by h. In both cases, we find get 0. So that means partial derivatives do exist at 0, 0. So the next thing is to determine the continuity of partial derivatives. So we need to compute the limits of the partial derivatives as xy approaches 0, 0. So if we take the derivative of the function of x with respect to x, which means we're going to take the derivative of this function, we end up with basically absolute value of y times x divided by x. And this would be for x not equals 0. Remember earlier we discussed this function. We know that this function is not defined at x equals 0. Similarly, we do the same calculation, but now take derivative with respect to y. In this case, we end up with this function. Again, this function here is not defined at y equals 0. That's why we mentioned here y not equal to 0. All right, so now I write this out here in more detailed form. All right, and again, we mentioned this is not defined. So if we now take the limit of this, right, with y going to 0, right, then this is 0 and this is equal to 0. And we do that for this case. In this case, we have x basically going to 0. And in this case, x going to 0. There's two different cases to consider. We get zeros. All right, so now look at the continuity argument. The functions f of x and fy are continuous to the point 0, 0, provided the following rules are satisfied. Back to the rules for continuity. F of x and fy are defined at 0, 0. The limit of xy approaching 0, 0 is of fx and limit fxy 0, 0 of fy exist. And thirdly, that the limit of f partial x is equal to fx 0, 0, and the limit of f partial y is equal to fy 0, 0. I mean, f of x 0, 0 and fy 0, 0 already have been pre-calculated, so we know they exist, but are the limits the same? Conclusion, con exists for both partial derivatives since all three continuity rules are satisfied. We just shown that this was 0, and this was pre-calculated to be 0. This was 0, and that was also pre-calculated by 0. So everything is okay, but only at the point 0, 0. All right, so the third thing is partial derivative existence on an open set. All right, we know we have a problem here because x over x naught, if y is not equal to 0, does not exist along the x-axis, except at the origin, which we already discussed here. And this x divided by absolute x divided by y over y absolute does not exist along the y-axis, that's at y equals 0, except at the origin. The conclusion is that the partial derivatives are not defined on an open set, therefore some of the conditions of theorem 15.5 are not satisfied. Now if you want to look at the partial derivatives of these functions, basically I've got a little interactive module here that you can look at. Here's the picture, a smaller version. So this is f partial x and this is f partial y. Help you visualize what's going on. All right, so the last slide is a fourth example, applying the definition for differentiability directly. So we're going to prove that the function fxy cube root of xy is not differentiable at the point 0, 0. So first of all, we have to determine the existence of partial derivatives. So we do that using the formal definition of taking a partial derivative. And it turns out in this case, we get a limit of 0 for fx and a limit of 0 for fy. So the outcome is that both partial derivatives exist. Next thing we have to prove is the existence of a limit and that that limit be equal to 0. So the error is going to be the difference between the function at the surface minus a tangent plane approximation, and again at the point of interest. And so we've written out as two terms. This is the function, and this is the expression approximating a tangential plane at the point of interest. So here basically is the limit that we have to compute. E of d, after doing this calculation, will be found to be this. And d, again, we defined as the norm. A is 0, b is 0, and so this becomes the square root of x squared plus y squared. And we determine if the limit of this exists. So we have to basically make an assumption now as to whether or not we think the limit exists or does not exist. We're going to assume it doesn't exist. If it works out, great. If not, then we have to go and think whether or not it does exist or not. All right, so we look at this one and we also notice, maybe we can choose y equals x. Let's see what happens. All right, so if we choose y over x, y equals x, then we end up with making the substitution. We end up with this on the numerator, and we end up with this on the denominator. And this can be simplified further as 1 divided by root 2, x to the power 1/3. Now if x goes to 0, this goes to infinity, which means essentially it does not exist. The limit does not exist and does not equal 0. Therefore, conclusion is the function is not differentiable at 0, 0. All right, so that concludes this lecture. That is lecture 4B. Thank you for listening.